Okay, let's begin. I'll now share my screen. Hey, what happened? Sorry guys, there's some delay. I think my computer is hanging a bit. So, is my presentation visible to all?
Yes, it's visible.
Yeah, it's presentation mode, right?
Yes.
Okay. So, let's begin. So last week you guys had asked a doubt regarding the this thing, right? One was HCP and FCC reverse. Like what happens if reverse loading is given? So that one and slip across grain boundaries and slip direction, right, that cup cone formation. So I'm sorry, like I couldn't find the answer so far. Like whatever I saw, it wasn't very convincing for me. So please give me some more time. I'll try to look into it and I will try to solve that problem. So, but I'll keep it in mind. Don't worry. It will be there, and when I figure it out, I'll share it here in the PPT. So today we will be seeing about XRT theory and problems. Okay. So just a minute. So do you guys remember what we saw in the previous class?
Defect, sir. Defect
Yeah.
dislocation.
So we saw about the various defects and dislocations. Okay. So in this defects, like what all would we see?
Point defect, line defect.
Yeah, we revised the point defects, right?
Yes.
Point defects are shortcut and frankly कुछ नहीं
Yeah,
पता.
yeah, Frankel and Schottky. Yes, yes.
Sotki.
Yeah,
Barger's vector.
Frankel, Schottky. Then,
Barger vector.
I'm sorry, I didn't get you.
Barger vector. About Barger vector.
Then
Yes,
line
yes.
and
But
edge.
that doesn't come under point defect. Sorry.
Uh, no, sir. In line defect, they will come edge dislocation and screw dislocations.
Exactly.
But
So there is line, and then underline we saw edge and we saw screw. Okay.
in which the Berger vector is एक में parallel, एक में perpendicular.
Yes, yes, yes. Work character. Do you know which is parallel? I mean, which is perpendicular? Any idea?
Screw में parallel है और edge में perpendicular.
Perfect. Screw is parallel, edge is perpendicular. Mm. Yes. Anything else we saw last time? So we also saw about the slip plane
The planes.
and slip direction. So the combination of these two gives the
System.
slip system. So we saw this last time, and also we saw about dislocation movement in edge and screw, and then we also saw about um, what are the sorry surface defects. Oh, yeah, and before that we saw about um, slip in single crystal and polycrystalline materials. And we also studied regarding the CRSS and why it's best at 45 degrees. So don't worry guys, just give me some more time. I will find out the answer to that particular problem. Then also we saw uh, polycrystalline materials, the difference between single and polycrystalline, and also we got to see what else, basics of X-ray. Okay. Uh, so today we'll be seeing deeply about the XRD and its related problems. So just a minute. Okay, we discussed this. Then we discussed the line defects, effect defects, volume defects. Also we saw. So volume defects is nothing but
Twin boundary.
yeah, yeah, grain boundaries. No, that
Twin boundaries.
yes. Tell me.
Twin boundaries.
Yeah, grain boundary actually comes under surface defects. So grain boundaries come here, but volume defects is pores and holes, pores, cracks, and
And blow.
holes. Yeah. So these are the things we saw. Um, okay. Now in today's class we will see little bit. I mean, we'll just revise about X-ray production. Then we will see about X-ray diffraction. Then we'll see constructive destructive interference, Bragg's equation, how to determine the lattice parameter of a particular crystal and find out what that crystal is using XRD, and then determination of grain size or crystal size using the XRD. Then I think the Scherrer formula is associated with that, so we will go into it. So already in the last class we saw like what are X-rays. So they are just nothing but electromagnetic radiation. So they are of very small wavelength. So since they are of very small wavelength, they are having very high energy. And since they have very high energy, they are very penetrative. So I think this is the Lord Rayleigh's formula, I guess. Lambda, sorry. Mu is equal to 1 by lambda power 4, I guess. So this is the uh, relation between wavelength and frequency. So am I correct? I think this is Lord Rayleigh's equation. Okay. So because of this difference, there will be
Equal to C by lambda.
yes, C by lambda, right? Sorry. Mu is equal to C by lambda is there, but then one more equation will be there. That is also
Equal to H.
uh,
Equal to H nu.
H nu is also there. E is equal to H nu is also there. This is photons equation. Okay, I'll look into that Lord Rayleigh's equation and will let you know. Sorry, that's for black body radiation. Sorry, sir, not for this. Yeah, this is the correct equation. So mu is equal to C by lambda. Okay, the relationship between frequency, wavelength, and the speed of light. So, but this is, I think, this only applies to photon. I don't know whether this applies for, because the C is speed of light. Uh, okay, I'll just check this and I'll let you know again. Okay. Now coming to this X-ray scattering. So what happens is um, incoming high energy electrons dislodges K-shell electron in the target. So what happens is, see, we usually have a machine where you have the filament. Okay, usually this is the cathode filament, and then here we will have the anode target, and then we will have the sample over here. Okay, so usually what happens is the cathode filament, I believe, will be tungsten, And anode target, most probably we will use copper or molybdenum or some material. So in our cases, let's take copper. So what happens is when we heat this particular tungsten material, okay, so this becomes uh, filled with electrons of very very high energy, and they travel towards the anode, and they strike the anode at very very high speeds. So when they strike the anode at very very high speed, what will happen is, you know about the Bohr's theorem, right?
Yes, sir.
So in the Bohr's theorem, what will happen is, say if this is a particular atom, okay, it is composed of different types of shells. So K, L, M, and N, O, like that. So they are all electrons at different energy levels. Okay. So what happens is, X-ray from sorry electrons from the tungsten, okay, they come at very high speed and they knock out electrons from their original orbital. Say, for example, if someone say there is an electron in the L shell, okay, and then this electron from the tungsten, okay, comes and strikes it, okay, what happens is energy is lost, and the electron comes from L shell to its lower energy state K shell. So when the electron transitions from this state to this state, that is from the L energy to K energy, what happens is electron is released. So if it transition is from L to K, then it is called K alpha. Then in case the transition is from M to K, then it is called K beta radiation. Usually for our experiments, we predominantly use copper K alpha, as it always gives the highest intensity as compared to K beta and K alpha. Yes,
Sir, released electron, where it is from coming?
from the cathode. So wait, I'll show the thing the next. Yeah. So this is the mechanism usually. Uh, this is the tungsten filament. Okay. So what we do is we electrically heat this. So we supply very high energy to this. Because of this high energy, a lot of electrons will travel here, and as a result, this will become very much heated up and a full region of high energy. And then we have the target over here, and then what will happen is, because of the high energy, the electrons will move towards the target and they will impinge on the target at very high velocity. So this target is usually the anode and of opposite charge. So it will attract at very high energy, and then there will be a collision, and during the collision, this is what happens. Uh, you got it, right?
Yes, sir.
Yeah.
Hello, sir.
Yes, yes.
Means is there sparking happens?
Usually sparking doesn't happen. More of heating happens. So you're saying, wait, you're saying this region, um, sparking here, or like spark traveling like this?
Traveling.
Traveling, yeah, electrons, yes, electrons if they travel, yeah, you will have a spark actually. So, but the thing is, the X-rays that are coming out will be invisible. So I'll try to see if I can get a video of what happens inside this particular chamber. Um, whether you can visibly see the sparking. Um, but I think there is, because there is a travel of electrons. Yeah. Uh, Also, once the electrons strike the particular target and they release the X-ray radiation, they will just scatter on all sides, and then they will be usually released through the beryllium window. Okay, and from the beryllium window, they will fall on the sample that we keep, either here or here. So here is another yes. So here is another image uh, where we have the cathode and then there is the anode. This is the target. Okay, and then when we charge it with the electrons, this becomes very high energy, and then the electrons travel from this electrode to this electrode, impinge, and then that causes your X-ray formation, and this is your sample.
Sir, X-rays are neutral.
Neutral, you are asking about charge, right? Yeah,
Yes, sir.
because it's like, right, sorry, X-ray, light, they are kind of similar when it comes to charge. Though like they have different phenomena, like light has photoelectric effect. It
But sir,
is
so for X-ray we have used like मतलब जब 12th में पढ़ा था तो इलेक्ट्रॉन माइनस यूज किया था और अल्फा रेज के लिए वो हीलियम प्लस प्लस.
Sir.
yes, yes,
Actually, how could X-ray be neutral? Because it's an throw up an electron source.
yes. No, the thing is, what happens is once the X-ray knocks out, right, you only get the radiation outside. So we have different orbitals, no? Atomic orbitals. This is the nucleus, and we have the electrons. So when the external X-ray comes and knocks out this electron, or uh, it usually knocks it out, and then it travels from higher energy level to lower energy level due to decrease in energy, and as a result, the thing that comes out is radiation, energy, just energy. So this energy will be neutral in charge. So it is only energy, like no charge is coming out, no electron, no ion, sorry, no ion, no electron or ion is coming out.
Sir, what happened to the incoming electron from the cathode?
So incoming electrode, I think usually, this being a positive charge, it may develop, deposit on this particular anode. It may be that case. So I don't know exactly like what happens, whether it leaves the system or it still stays there. My guess is like it may either get absorbed by this anode, because this is positive charge and electrons, as we know, are negative, and you know or it may be like released for a small distance around the uh, electrodes, say anode. So that is my guess. So most probably it will be, I think, mostly absorbed by the anode. That's what I'm
Okay.
thinking. So just a second, note it down. So why? Okay. What happens to source electrodes? The source electrons. Okay, then. Yeah, just check it and right. So, but you guys got the general idea, right? What happens during X-ray, like X-ray formation? Is it clear to everyone?
Yes, sir.
Okay. So next, I think we already saw this. So X-rays for NDT. How different X-ray images are no, show different results. So all of this are X-ray technique only. So first thing we see, lack of penetration. The edges have not been welded. So I think there is some sort of defect in welding. So I think there is improper penetration, so we are unable to see the full weld structure properly. Then here we see interpass slag inclusions. So here I mean, here we see that the weld is perfect without any problem, but there is a problem with the X-rays penetration. Here, there are some defects, and they are clearly visible in the X-rays. So usually in the X-ray, if a particular material is harder, the atomic number is harder, or atomic number greater than source atomic number. Sorry, source atomic means target atomic number actually. Then the image will be whiter. So as far as I know, this is the usual phenomena. So in case the atomic number is not as high as the target's atomic number, usually as we saw it is copper or molybdenum or something like that, uh, it will usually become darker. So here we saw some slag, and that is picked up by the uh, X-rays. So there is a clear difference between the pure metal and the slag, I believe, due to the difference in the atomic number. And also here there is a cluster porosity. So since there are pores here and there, they are appearing as dark spaces, dark spots on a white image. So that kind of shows us there are pores, and like there are open areas. As a result, that place is dark. Next, there is the what can I say? Deposition of a material which is whose atomic number is way higher than that of the parent material and the target material. So since the material that is deposited here is tungsten, it's very bright because its atomic number, sorry, not atomic, what am I saying? Atomic weight is greater than uh, this particular sample and target. So only it is appearing as very white spots. Then transverse crack. So a crack or fracture that is noticed over here. That is due to, I mean, because of a crack, there is nothing there, right? No metal continuity there. As a result, it will appear black in the X-ray vision. So these are the components of the X-ray diffraction machine. So what will happen is here we have the X-ray source, okay, and then we have the filter. Either we can use alpha or beta. So usually we use alpha only. Beta is rare case. So alpha filter only we use most of the time. Then there is divergent slit. Then mask. So like, these are all accessories. Then we have the goniometer. So the goniometer is like sample stage. Okay. So sample stage which is adjustable. And then we have the detector. Okay. So what happens is X-rays come through the source, falls on the sample, gets reflected, so diffracted, and gets detected by the detector. So this is how it kind of looks like. Um, this is the target, and from the target we get our X-rays. They fall on the sample and they get detected in the counter or detector. Okay, so this is the, I think in this machine also, I think it is pretty obvious. Like from this you can see that this is the source. This is the, yes.
As a source, uh, we use cesium source, right, sir?
Yeah, different sources can be used depending on material. So as far as I saw, like most of the papers they used copper K alpha. Cesium can also be cesium, molybdenum. So for that, they will change the source material target.
In pipeline industry, most of them are used cesium source
Oh, for
ions.
okay, okay. For X-ray, you're saying X-ray itself. X-ray
Yes,
for pipeline crack detection.
yes, sir.
Ah, yeah, that may be true. Yeah. I'm saying for XRD, that is X-ray diffraction experiment, they usually
Okay,
use
okay.
copper K alpha. But yes, the thing varies. I think in medical applications they use lead. So medical application they use lead as target, I think. And for yours pipeline, huh? Pipeline, I think they use cesium. Okay. So thanks for sharing that information. So this is the XRD machine. So this I think, I mean, this looks like the source, and this has to be the detector, and that is the sample table. Okay. So we will come to the XRD analysis of the polycrystalline material like later, but this is just to give a small insight. Like this is the same sample only, but at different planes, we are getting different peaks, and from these peaks we will index them, and from that we will find out what kind of material it is. So in modern uh, detection technique, there is this software called expert high score. So with this software we will be able to find out the we will match the X-ray peaks with the standard peaks in the library. So either they may be JCPDS or ICCD, one of these two databases. So I think this is a Japanese database, and this is the International Crystal Database. So this is how we usually analyze polycrystalline materials, or even single crystalline for that matter. And here we can see, like for polycrystalline materials we will get a slightly broader peak, whereas for single crystalline materials you can see there's a red color lines now. We will get a nice sharp red color line. So usually if we want to find a new material, better to study its properties as a single crystal first. So single crystal usually gives perfect information regarding new materials crystal structure. And the database will always contain the XRD data of single crystals only as a reference. Okay. So next we will go into the X-ray diffraction. Um, when we take this particular cube, so I think this is a body-centered cubic structure. Okay. Uh, what will happen is we will divide this particular uh, X-ray, like a cube, into uh, planes, various planes, and we will allow the X-ray to interact with these planes, and then we will study uh, what sort of interaction is occurring. And while the X-rays are falling on this particular material, right? Sorry, on these planes, they must usually be in phase. Okay. So in phase means, uh, say if uh, there is some wave coming like this, okay, the corresponding wavelength here also should be same. So only then will we be having what we call constructive interference. So this is in phase. Okay, both waves should be in phase. Though there are like many planes, usually we for theory we will only consider two planes. Okay, so if we consider for two planes, we can extend that to n number of planes. In case the waves are out of phase, then we get something known as destructive interference. Okay, so here it is out of phase, right? So in destructive interference, we get no peak at all. In constructive interference, we get a intense peak. Okay, so here we can see this is a refined X-ray image, XRD image. So all these places that you see over here, all these peaks are due to constructive interference, and all these trough-like areas, flat lines, they are destructive. They are due to destructive interference. Okay, this is constructive interference. Okay, so here again I have written in detail. Mm. So it is constructive and destructive interference. We just saw it in the previous slide. Okay, so the thing here is in constructive interference, uh, it must be made sure that the phase is perfectly in line, even if it is a little bit out of phase also. Okay, say for example, uh, we know the Bragg's formula, right? In lambda is equal to 2d sine theta. If this n, okay, that is the uh, order of diffraction, if it is of the order 1, 2, 3, 4, etc., okay, as whole numbers, then we usually get uh, an intense peak as output. Okay, uh, say for example in this place, okay, the wavelength here is lambda. Okay, the energy here is lambda, and lambda equal to 1. Whereas here what we are doing is we are increasing the frequency of the wavelength. So here instead of 1 lambda we are having 2. So sorry, here n is equal to 1. We will be having 2 wavelets. So n will be 2 over here. Okay, due to higher frequency. And then further we are increasing the frequency, means n equal to 4. It will look something like this. So the thing is, in case we are having something like n is equal to 1 by 2 or 1 by 4, there usually is no peaks. So how do we get this n value? That we do through our Bragg's equation. So Bragg's equation, you already, I think, will be knowing this formula. N lambda is equal to 2d sin theta. The thing is, let us take a particular X-ray, okay, striking two planes. So let's say this is ray 1 coming like this, and ray 2 also coming in phase. But the thing is, it will end right here. Here what will happen is, once the ray 1 strikes, it will diffract and it will keep traveling. But here what happens is, there is a space, okay. So usually uh, an extra wavelet is required, I believe. So yeah, usually an extra wavelet is required, a full wavelet actually. Extra wavelet is required for maintaining it in phase. In this region, if there is any problem, okay, if the order is lesser than 1, in that case we may not get output or peaks. So we'll just go to the Bragg's equation as to how we got it. So just a sec. In this blank space, right, to find out this particular relation, this particular formula, right, with which we can determine whether or not peaks can be formed, okay, what we do is we draw. So here with the ray 1 thing ends, right, the wavelet ends. So from this ending to this ending, we will draw a line. Likewise, here also we draw like this, means in equal angle. Here we draw another line. Then we know that this distance over here is d, right? But we do not know what this is, okay? And we have to find this. So what we should do, we should find AB plus BC, which is the missing wavelet distance. We can also call it path difference, because there is a difference in path between this and this, right? So that path difference is AB plus BC. So AB, as we know, is d sine theta. How is it d sine theta? So we know sine theta is opposite. Opposite is AB by hypotenuse D. So we get AB equal to d sine theta, and likewise BC is d sine theta, right? Now to find the path difference, or I'll put PD here, AB plus BC, we get 2d sine theta, right? So the number of wavelengths, the order of diffraction, that is uh, the order of wavelength striking here times the wavelength is equal to 2d sine theta. So is this okay, guys? Is this a bit clear? Any doubts? Can we move on? Uh, am I audible?
Yes, sir. Perfectly audible.
Okay. This is clear, right? The Bragg's equation and the interference constructive testing. Okay. So I mean, just if you know the formula, that's enough. So theory and all, like it's not that important for gate. So formula is important. And then what you have to know is for X-ray diffraction indexing, different cubic or say different structures, simple cubic, body centered cubic, FCC, even HCP structures also, they have different types of reflections. So from multiple observations, what scientists have concluded is they used simple cubic for basic uh, what can I say, basic plotting of these intensities, and from that they got the Miller indices. So this intensities actually means basic plotting of uh, the waves. Okay. For BCC, if you require, you have to add the H plus K plus L, and that number should be even. For FCC, the H, K and L should either be all even or all odd. So we will come to that in the next slide. So this is the value for interplanar spacing for the different various crystal systems. Mostly you just follow cubic and hexagonal. So mostly the questions will come from either cubic or hexagonal. Others usually will not be asked. So here you see here we have uh, the HKL, the peaks, okay, and they are for the simple cubic is taken as the base reference, okay, and all the peaks are indexed. So we will see how they are indexed in the next slide. As of now, just know that they are all indexed. So if the HKL is just remember this order, okay, 100 110 111 200 210. So simple cubic will usually give an output like this, whereas if it is face centered cubic, right, then what did we see? We saw H plus K plus L should always be HKL should either all be even or all be odd. Okay. So here if we see FCC means here all are odd, right? So this will be considered as first peak, and here all are even. So 0 is also considered as even. So here all are even. So this is also considered as another peak. So this is the FCC second peak. Likewise, this is third peak, fourth, fifth, sixth, and seventh peaks. Okay, so this is for FCC case. For BCC case, if we add all these, okay, 1 plus 1 plus 0, that should give even. So here 1 plus 1 gives 2. So this is our first peak. Here 1 plus 0 0 means 1. So 1 is odd. So odd means nothing. So 1 plus 1 is even. So this is taken. Likewise, this is 3 odd. And then this is also even, 2, right? So this is the second peak. And then this is 4. This is taken as third peak. Likewise, BCC's peaks are identified. So I'll give you further clarity through a problem. Okay. So I think that comes next. Before that, we'll just look at the X-ray diffraction application. We already know that it's used for crystal structure, then determining lattice parameters, grain size, microstrain. So these things I think we'll discuss towards the end. Then for we already saw this identification of say cracks and pores. So non-destructive testing. NDT is non-destructive testing. Sorry. So for all
Sir,
this there is
why it was called radiographic testing?
radiographic. Radiographic means Usually they refer to using electromagnetic radiations for imaging.
Yes, sir.
So that's why usually it's called radiographic tests, not using radio
It,
waves.
it has nothing to do with radios. Okay.
No, 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 not using radio waves. Yeah, that's usually a problem. But I don't know why they called it like this, because it's really misleading. But this is the
But
correct.
for while they test, but they use an radioactive machine where they measure that how much
Exactly,
radiation.
exactly. So measuring radioactive material. So for that, perhaps they use radiography. Yeah, very good. Okay, coming back to this. So again, XRD is also used for identification of phases, then residual stress, textual transformation and all. So I think all these things will be covered, and I don't know whether we will cover today itself, but maybe at least in next week's class, we will cover grain size microstrain identification of phases. So as of now, we will first find lattice parameter determination using XRD. So what is happening is, we are okay, what we are doing is, we are taking our sample. This is our sample table. We are keeping the sample here, and then we are firing x-rays, and it is diffracting. It's going to the detector. Okay, and this we get a reading from the detector like this. Okay, so 38, roughly we are getting some reading like this. That reading is what is tabulated over here. So my question is, from this, can we find the crystal structure of the material? Is it possible?
Yeah, sir. 9 peaks we are getting, so we can say that it is FCC.
So 9 peaks. So we are saying FCC. Okay. Before I go on further, I would like to say that the answer is absolutely correct. But how can we say from the peaks itself that it is FCC? Like number of peaks that are present.
I don't know, sir. मैंने तो तुक्का मारा था.
Okay, so I think you saw from this previous slide, is it? But even then,
इसके अकॉर्डिंग तो BCC होता है. वो गलती हो गई.
yeah, that's true. Here, if you look, it's BCC, but
Copper, sir, being the soft metal also, it is
uh,
FCC only, no?
no, no. See, the thing is, here we are using target, and we don't know what metal it is actually. We don't know what metal.
So
We are
it
just
is,
getting
no,
the
it's recorded with copper K alpha radiation.
yeah, yeah. It's recorded with copper K alpha, but I want to see what material that I'm using. Unknown material. Okay, this is unknown.
But in comparison to that, by using that wavelength or that peak, can't we say that which crystal is that? Like maximum peak would be heat on the surface or on the crystal layer.
Yeah, that is actually the fundamental idea, what you're saying. But the thing is, this is a theoretical approach. What I'm doing right now is a theoretical approach. So, okay, since time is running out, we will go for that. This is the usual way, as far as I know, to find out the uh, particular crystal structure. I mean, we don't know what material it is, but the crystal structure, if we look from here, is FCC. So you may ask how that happened. First, we are getting these peaks, right? So we are calculate from this. What we do is, from 2 theta value, the graph, in the graph, we only get 2 theta and not theta. We should be very, very careful. The answer that we get will be in 2 theta only. I mean, sorry, the values that we get will only be in 2 theta, not just theta. So what we have to do is, we have to divide all of these answers by 2 to get the theta value. Once we get the theta value, what we should do is find sine square theta. Okay, sine square theta for all of these peaks that we got. Okay, this is roughly the sine square theta of all these values. Then what we do is we do the sine square theta of a particular value divided by sine square theta of the minimum value. Minimum value is the first peak. Okay, in our case it is this one. Okay, this is our theta minimum. So what we should do is sine square theta by sine square. This is not sine n square. It's just sine square theta min. Okay. Say for finding the first value. Okay, this one. What are we doing? We are having. Sorry, I'm getting a call. Okay, just a minute. Yeah. What we are having. What we are doing is 0.1088 divided by, sorry, 0.1088. So this is, I'm taking the first value, right? First peak is 0.1088, and among all these value, theta minimum again is 0.1088. So the answer is 1. So we get the answer over here. Likewise, we have to do for all of these theta values. So theta min 2. Okay, I don't have much space here. So we'll just finish this problem and then I'll leave you guys. So say sorry, theta 2, not theta min 2. Theta 2 is equal to sine square theta 2 divided by sine square theta minimum. So that is 0.1450 divided by 0.1088, which will give me 1.333, which is this particular answer. So you guys got how this particular table is formed, right? Sine square theta divided by sine square theta min. Is this clear?
Yes, sir.
Okay. So after that, yeah. After this, what we do is we are having 3 parameters, right? H, K, and L. Since we are having 3 parameters, the value that we are obtaining here, we are multiplying by 3. And that's how we get all these values. Okay. Then what we do is we will do the h square plus k square plus l square. The value that we get over here, we assume it to be h square plus k square plus l square. Okay. And then we just round off all the values. If it's 3, it's 3. If it's 3.9 means we'll take it as 4. 7.9 means 8. Anything 0.5 and above, that we will consider as the higher number, and anything 0.5 and below, that we will consider as the lower number. Okay.
बट सर 9th कॉलम में तो उल्टा कर दिया है.
Yes. Okay, okay. So even here, yeah, 23.045, it says 24. So okay, in that case we will do one thing. We will consider like anything, if it's point something itself, we will take as a higher number. Okay. So because here it says 23.045 itself, it is 24.
Sir, it should be 23.946.
Oh, 946.
Yes, sir.
Oh,
हाँ
okay.
सर.
So there's a mistake, I guess. Yeah. Yeah, in that case, yeah, it's correct. It's 24. So the thing is, all these numbers should be rounded up, and from this we will find the HKL value. So to get a value of 3, how we will get 1 square plus 1 square plus 1 square is equal to 3, right? So the HKL value we can take it as 111, right? So in case we want 4, so in that case what we can do, 2 square plus 0 plus 0, that will give us 4, right? So we'll put the HK value as 200. So this is h square plus k square plus l square values. Okay. Likewise for 8, 2 square plus 2 square plus 0, which gives you 8. and then for 11, 3 square plus 1 square plus 1 square. So from the values that we get over here, we are able to index the various planes. So you got how the index is happening, right? Any doubts here, guys?
Yes, sir.
So did you get what is happening here? Like how these planes are indexed?
Mhm.
Index means like how just from the peaks we are able to get the Miller indices. Did you guys understand this particular point? I mean this particular problem?
Yeah, sir.
Yes.
No problem, right? I mean it's understandable, right?
Yes.
Because
Yeah.
this is very very crucial because this application. So from the just the theta values, you will be directly able to get the Miller indices, and once you have got the Miller indices, there is this formula, right? Lambda square by 4a square is equal to sine square theta by h square plus k square plus l square. So with this formula, sorry, we can be able to determine the lattice parameter, that is a, lattice parameter of the unknown crystal. Okay, so we were able to find out and also the HKL pattern here. So first we have 111, then 200, then 220, then 311. Usually this is the pattern of FCC. We saw in that previous table, right? So since this is the pattern of FCC, we can say that this particular material that is recorded in XRT is a FCC material, but we don't know what metal it is or what material it is as such, but we know for sure crystal structure is XRD, and from that we calculate the parameter, lattice parameter, through this formula. Okay, we get, I think the answer is around about 4 angstrom or 0.40 something nanometers. So all this answer over here is in nanometers. So you got this particular problem, right? It's clear, right? Guys,
Yes, sir.
it's
Yes.
clear, right? Okay, okay.
Yes. Yes.
So I think it's already time now, 7:05. So I'll end here. Sorry, guys, I didn't upload last week's recording in the drive, so I'll upload it by today itself. Okay, and also I'll upload this. In case there are any doubts in today's class, you can please ask in next class also. So it is clear, right, till now?
Yes, sir.
Yeah. I'll just sorry. I'll just provide the link. Just a minute. Yeah, this is the drive link. So is it opening for those who are new? Yes. Okay. Okay. So I'll you can please save this link. I will constantly keep uploading materials here, and I think it will be visible as I upload. So thank you once again, guys, for joining with this week. I'll upload the recording and the PPT of last week and this week by today or tomorrow itself. So we will see next week, guys. And next week, hopefully, I will try to find the answers to all the doubts that you asked in the previous week and this week. So thank you so much, guys, and wishing you happy New Year once again.
Thank you, sir. Thanks a lot.
Thank you, Archit. Thank
Sir,
you so much.
one
Thank
thing,
you.
sir,
Hey,
one thing can you do for us? Like,
yeah,
regarding this topic, if you kindly provide as such get related problem, numerical problem, or any questions, MCQ based questions, that would might be helpful because uh, as the exam is knocking on the door.
sure, sure. I will do that. From in next week, we will solve some more problems from XRD, and not just XRD, related to XRD also, like the linear density, the theoretical density. If it's there in the the gate previous year problems now. We will solve that. And also, if you are unable to solve in class, I'm preparing one notes. So I told you it will take, I think, some more time, maybe 1 more week time. I will prepare the notes and I will update till we have finished, like whatever we finished till now, till XRD problems. And I will upload in the same link. So whatever
Okay.
we have not discussed in class, those questions and explanation will be there in that particular notes.
Thank you,
Sure.
sir. Thank
Yeah.
you.
Thank you so much, Avijit. Thank you.
Thank you.
Thank you, sir.
Thank you. Thank you, Srinivas. Thank you. Thank you, everyone. We'll see you next week.